Good afternoon, everyone. It's my pleasure to introduce our first speaker for today. Morgan's a native of Eden, Texas, in Concho County. Morgan earned her BS in 2019 from Angelo State University, majoring in ag leadership with a minor in animal sciences. And Morgan's currently working towards her MS in agronomy here at Texas A&M University. Shortly after Dr. Reagan Noland started in his position as extension agronomist in San Angelo, he emailed some of his colleagues at the ag department at Angelo State University to inquire about any potential student workers. And within minutes of him getting in touch with those individuals, Morgan called about the job. And she quickly became an essential part of Dr. Noland's program in San Angelo. And as a student worker, she studied, tested, and earned her Part 107 license to operate their program's UAV. Dr. Noland shared a few comments with me about Morgan that I'd like to share with the group. Dr. Noland says Morgan's outstanding work ethic, ability to learn, and sincere interest in our work made her an outstanding candidate for a graduate program in agronomy. Morgan represents our program very well and has placed multiple times in state and national level graduate competitions, and she continues to grow and progress as a scientist. So today, Morgan's going to be sharing some of her research on nematode management in cotton, utilizing remote sensing. So, Morgan, it's all yours.
Thanks for that introduction. So as you said, we'll be taking a look today at informing reniform nematode management using UAV technology. So jumping right into it, the reniform nematode is going to be our main source of biotic stress for our experiment. The reniform nematode is a soil-borne pathogen that exists in very large population sizes once it's actually become established in the field. Again, they are microscopic, and so in just one Ziploc baggie of soil, you can have thousands of nematodes. And so it's really important to think about when you're doing things like sharing equipment with your neighbors, or even just driving through the turn rows or walking through an infected field with things like your jeans, cuffs, stuff like that. So you can suppress populations by rotational cropping with things like corn or sorghum, but all it does is suppress. And reniform nematodes can stay dormant in ideal soil conditions for over 2 years. So again, rotational cropping only suppresses and it doesn't eradicate the problem. One of the main problems with diagnosing reniform nematode problems is that a lot of the above ground symptoms are similar to other stresses like nitrogen stress or irrigation stress, which we will be implementing to try to separate between the two. Taking just a quick look at the background, in a report done in 2018 for Texas, reniform accounted for over 10% of bales lost due to disease. And something to think about when you look at the 10%, that's already a pretty big number, but that is not accounting for any reniform fields that may be flying under the radar, because again, they are hard to diagnose. So that number could be a lot bigger than we know. We do know that reniform nematodes do not affect fiber quality, but they do decrease boll size and the number of bolls per plant, which in turn drastically reduces yields. Nematode pressure also increases cotton susceptibility to outside stressors such as other diseases or again, nutrient or water stress. Traditionally, nematodes are controlled using nematicides, but they're not very selective in the soil and they can be dangerous to apply. And they've been shown to produce very inconsistent results based on when you apply them. So in recent years, there has been new genetic resistance released on the market that has been proven to be a more reliable management option. The previous grad student before me, Jenny Dudak, she conducted some variety testing that compared reniform resistant varieties to root knot resistant varieties, as well as susceptible varieties. And then there were multiple nematicide applications along with those. And the main takeaway from this experiment was that genetic resistance is consistently more reliable when compared to things like nematicides. So root knot resistance was tested because there was some theorizing that maybe root knot resistance and reniform resistance kind of meshed together. They didn't find any proof of that in her research. And again, they saw that nematicides were very inconsistent across locations and years. So again, knowing that genetic resistance is such a reliable and consistent management tool, we wanted to know, when should a grower prioritize genetic resistance when choosing their cotton varieties for the year under different nematode pressures, nitrogen applications, and irrigation? We also wanted to know, can we improve the remote detection of reniform nematode presence and severity? And we'll be using drones to try to separate those stresses. So one of the coolest things that I think of when I think of using drones is that they're so easy to get a hold of today. So any grower can go to Target, Amazon, Best Buy, and pick up a drone for relatively cheap. And with a very minimal training, you could use YouTube tutorials to teach yourself how to fly and map your own fields. And so a grower, regardless of age, can sit on the back of their tailgate and map huge portions of their field in very short amount of time. And they can use these maps from their drone imagery to monitor infestations across the years and maybe see if their management practices are helping to reduce the infection. So to address our questions, we set up 2 separate trials. Our first trial was a variety trial that we set up in Snook, Wall, and Lubbock, Texas. And this tested 2 of our reniform resistant varieties, a Delta Pine and a Phytogen variety, against what we're calling 4 comparable industry susceptible varieties. And so that's a lot of words just to say that we chose 4 varieties for each location based on the race trial results that were performing well in the area, that were similar in maturity to our resistant varieties. Our second trial is only in Snook and Wall, Texas, and that's testing Phytogen 443, the resistant variety, to Phytogen 480, a similar maturing susceptible variety. We took soil samples and sent those off for testing, and we decided to use 0, 22, 45, and 67 kilograms of nitrogen per hectare, where 45 is our recommended rate. And we tested both of these trials in both irrigated and dryland conditions. All of our fields were flown using a DJI Phantom 4 Pro, and that is equipped with an RGB camera that is set on a gimbal on the front of the drone and a Centera NDVI sensor, which is fixed nadir on the back. We also had a SpectraWiz Blue Wave spectrometer that we used for the first time this year, and all of our flights were planned using Pix4D capture, and all of our imagery was stitched using Pix4D mapper. All of our image analysis was done using the open source QGIS. We had standard plot dimensions. They were 4 rows by 40 feet long, and all of our measurements, including nematode samplings, plant heights, stand counts, were all from our middle 2 data rows. Both of our trials were set up as a randomized complete block design with 4 replications. Our first trial, which is again the variety trial, was analyzed, both of them are in SAS, by the way, as a mixed model by location, where variety and irrigation were fixed and block was random. And we didn't combine locations only because varieties were different for each location. For trial 2, we combined across locations where variety, nitrogen rate, and irrigation were fixed, and location and block nested within location was random. We used 2 P's and an alpha of 0.1. Looking at all of the measurements that we took, our ground measurements included nematode sampling, and that was done prior to planting and mid-season at about peak growth. We also took stand counts, plant heights, and yields. Our remote derived measurements were all analyzed in QGIS, and that was canopy percentage, height, volume, and GRVI. GRVI is what we used as an alternative to NDVI, simply because we weren't able to use any of our near infrared data this field season, and so GRVI was our alternative. I went to Lubbock for a couple days, and I studied with Dr. Terry Wheeler. She's a pathologist that specializes in root knot and reniform research. She taught me proper sampling techniques and extraction techniques, and then we did lots of ID between different nematodes that are common in cotton fields. So we took 6 samples per each plot, again from the data rows. We mixed those all together and then pulled a subsample from the bucket for each plot in the trial. And that was done under moist soil conditions where we had easy access to the root zone. We used the pie pan method, which is a modified Behrman's funnel, to extract all of our nematodes. This is a gravity-fed method. Most commercial labs, like the Waters lab is one that we've used, uses centrifuge extraction. There's pros and cons for each of them, but we decided to stick with the pie pan method simply because it's what we were trained on, and it's a lot easier when you have a bunch of samples coming in at the same time. There's less hands-on time. And so as you can see on the picture on the right, it really is just a pie pan. It's a dollar store aluminum pie pan with chicken wire and a soil sample wrapped up in Kleenex. And you pour distilled water over it, leave it for 2 days, and then take the nematode solution out of the bottom of the pan and use that to extrapolate your counts. We were really ambitious when we started this project, and we really wanted to do a flight at each location every other week. We found out very quickly that the distance between Wall and Snook was going to be a problem because it's very hard to coordinate when to be in each location given ideal drone conditions. So one of the biggest problems especially was that in West Texas, by the time the sun is high enough in the sky to eliminate shadows and all of our imagery, that's usually peak wind in West Texas. And so it starts moving around the cotton plants, we get blurry imagery, and then a lot of the times it's just too windy to fly a drone. And then of course we had so much rain this year in College Station, that was also a factor. Our SpectraWiz Blue Wave spectrometer, I mentioned this is our first year using it. We had a lot of trouble calibrating according to light conditions. Anytime a cloud moves above you, over the sun, or even in the distance, it changes the light conditions and we have to recalibrate. We had a lot of trouble with that this year, and we're still working on how to fine tune that data. The Centera NDVI sensor, that was the sensor that was fixed at nadir, meaning that it doesn't rotate at all. And I did not increase the overlap. I set it at the same overlap as my RGB camera, which wasn't enough overlap, and we weren't able to stitch that imagery, which is why we're using GRVI this year. So looking at image analysis, this is what's called an excess grain map. And this is one of my first steps when I'm looking at my images and trying to separate data. So this is from Snook, Texas, which is at the farm out of College Station. On the left, this is a mid-season flight. And you can see a clear distinction between all of the alleys, the plots, and even in between the rows. And so I felt pretty confident drawing my boxes around each plot that I was only pulling data from each plot. The map on the right is the same field, but it's a couple months later in the season, and it's probably too late to be flying for image analysis. So you can't even see the alleys, let alone the plots. And so for the purposes of today, all of our image analysis is done using our mid-season flights. So this picture on the left, the green one, is what Pix4D Mapper kicks out to you when you stitch your imagery. And then I create the excess green map from the slide previously, and then I create a threshold of 1. And any pixel that has a value more than 1 is classified as Canopy Values, and anything less than 1 is designated as soil values. And so I'm able to isolate the soil pixels so that all of my analysis is done solely on Canopy Values. Now, jumping right into results, all of the results for this presentation are preliminary 2021 results. So this is just a significant effects table where we see that for variety and irrigations, we had some significance for yield, height, nematodes, and GRVI. We did have a nitrogen effect on GRVI and an irrigation by variety effect on height, as well as a variety and nitrogen effect on yield. So the top graph here is comparing the two varieties across all locations. And again, the top one, Phytogen 443, is the resistant variety. And so you can see pretty clearly on just this little table that the resistant variety is higher yielding, they're taller plants, and they have less nematodes below ground. And so you can see it's just under 2,000 nematodes for the resistant variety and over 4 for our susceptible variety. So it's really taking a hit there. Moving down below, this is just our irrigated versus rain-fed effects. We see pretty obvious trends where the irrigated plots are higher yielding, taller, and they're hosting more nematodes. Looking at the variety and nitrogen effect on yield, the darker maroon is going to be our resistant variety. And we had a kind of weird interaction where our recommended rate of nitrogen was actually lower yielding when compared to our highest rate of nitrogen. So don't have a great explanation for that one, but I think the important thing to note with this graph is that our susceptible variety, which is the lighter gray on the right, showed no changes with any of the nitrogen applications. And so regardless of how much nitrogen we pumped to it, didn't really affect yields. That leads me to believe that possibly in this scenario, the nematode pressure is what holding this variety back. So this graph is actually sliced by variety. And again, we see a similar trend where in our resistant variety in the dark maroon, it did increase yields with irrigation, but in our susceptible variety, again, regardless of irrigation, there was no difference statistically in height, and so again, we can theorize that possibly the thing that is limiting phytogen 480, our susceptible variety, would be nematode pressure. When we look at GRVI, these are turned weird just because they're negative values, but the graph on the left is our nitrogen effect on GRVI. We analyzed this data on a flight that was taken 2 weeks after our nitrogen application. And again, we didn't have our NDVI sensor, so this is purely using RGB, which is kind of like a GoPro camera. And we were able to separate our highest rate of nitrogen from the middle two rates. And the graph on the right is just showing the variety effect on GRVI. And so the shorter bar on the bottom is our resistant variety. And you can see that it is showing higher values for GRVI, which might indicate greener, healthier plants. When we look at our nematode effect, irrigation did increase nematodes, but there was a 54% reduction of nematodes in the resistant variety. And I mean, I think it's pretty obvious that the susceptible variety is just really not able to fight off any of those nematodes. And we see that in our heights and our yields across the board. So jumping into the variety testing, we had phytogen 443 and delta pine 2143 in all 3 locations. And then again, our varieties were chosen that were similar in maturity and high performing in race trials for the area. Variety did influence cotton yields at both Snook and Wall, Texas, but there wasn't any change with variety in Lubbock, Texas. So the graph is the summary for all sites. And again, we see the same trend where our susceptible variety, which is the two bars on the left, have higher counts of nematodes and lower yields. And our Reniform resistant variety has higher yields and less nematodes when compared to the susceptible variety. The 2 bullet points down low are just separated out by location, where again, we see that at Snook and Wall, Reniform resistant varieties were consistently among the highest yielding, but there was no change in Lubbock, and some susceptible varieties were still yielding similarly to resistant varieties. So bringing it all together, GRVI was affected by nitrogen rate, and we saw that as early as 2 weeks after application, just using a GoPro RGB camera. Our remote height measurements were a reliable alternative to our physical measurements. We had really high correlation between our remote measurements and our ground measurements, and so we feel confident using that next field season. Our plant height was a consistent indicator of nematode population that wasn't affected by nitrogen treatments. And again, across both the variety trials and our UAV trials, we saw that Reniform nematode presence is a consistent limiting factor to growth. And so if you're a farmer and you know you have Reniform nematodes in your field, you should maybe start planting some resistant cotton. This is just my works cited page. You want to take a grab of that. But I'd like to thank the Texas State Support Committee for Cotton Incorporated, Texas A&M Cotton Extension Program, and then Dr. Austin Dobbles and Terry Wheeler for training me. Thank you.
Good job. Parsons.
Is there any, good presentation, by the way, is there any yield penalty to growing a reniform resistant variety in a non-reniform infested field?
No, we saw in Lubbock had very low nematode counts throughout all the plots. And so we use that as our low nematode pressure. And they were yielding similarly to the susceptible varieties. So I don't think you're losing any yield for it, but you're not gaining any either.
So do you think cotton breeders are going to start moving all this resistance in all their varieties? Or
I would hope so. I think reniform is a problem that we're going to need to be addressing soon.
Great presentation, Morgan. I saw in your results that you mentioned multiple times that in your irrigated trials, there's an increase of nematodes. Do you have any idea on why that is?
Yeah, so good question. We did have higher populations of nematodes in our irrigated. And so just speculating, in our irrigated plots, we had taller plants that were higher yielding. They had more above ground biomass, which would translate to below ground biomass. If they have healthier root systems, I would assume that they're able to support higher populations of nematodes.
Great presentation. So you obviously had a lot of factors playing into your trials. Did you do anything to start your nematodes or your nematode populations off at a consistent level, or how did you analyze your data going forward, incorporating the fact that there may have been differing levels of nematode populations to begin with?
Yeah, so to address that problem, that's what our preseason nematode counts are for. This year and in previous years, we've taken them by range. And so we've just very broadly going per range for each plot and use that as our preseason counts to calculate a delta nem effect is what we call it. We are going to start doing preseason samples per plot so that we can fine tune the change in nematode populations throughout the season.
Great presentation. I was just wondering, did you look at any other vegetative indices? And like, how do you stick to the one you found?
So we really only use GRVI. We were going to use NDVI just because it's common, but because we didn't have near infrared, we chose GRVI. That's really the only reason. And with QGIS, we have all the data that we can look at other vegetative indexes. We just haven't yet.
Curious, is there like any natural predatory species that control nematode populations under normal circumstances?
Yeah, so there are, Reniform nematodes are considered plant parasitic, and there are other nematodes that are parasitic to nematodes, and they have little hooks in their mouths and they hook onto the others and get rid of them, but we haven't tested anything with that.
The question I had was, what is the mechanism of reniform resistance? Does it kill the nematode? Does it keep it from reproducing? What's the resistance mechanism?
So as far as I know, and I do need to read more into this, but it just prevents the relationship. And so reniform nematodes, the females have to reproduce in cotton roots, and the resistant varieties prevent that relationship. I don't know the specifics on that, and that's something that I need to look more into. But it just stops them from reproducing or discourages them from reproducing.
So using the remote sensing platform that you use, do you feel like you could build a model to detect, like machine learning model to detect? 'Cause I saw that you saw differences with height. So maybe using GRVI and height to kind of detect the nematodes before? Yeah.
So in the long-term goal, yeah, that would be super cool. That's kind of our focus is seeing which above ground measurements we can use to isolate reniform stress.
Just a follow-up to that question. So how do you differentiate the vegetative indices if the constraint is not coming from root knot nematode?
So currently we can't. And so that's why if I might be answering wrong, I'm so sorry. So you can't, and that is why we are taking so many other measurements that may not correlate with reniform stress so that we can remove. So for example, GRVI was only affected by nitrogen rate because it makes them chlorotic. And so we can't yet, but the goal is to find enough things that are specific only to reniform that we can isolate it.
Let's see what the Chativerse has to say. You can read Megan's question.
Yeah, so they're asking if you can monitor, if you can take several pictures during a season and compare the effect of nematodes over the entire growing season. So just by the eye, you can. Reniform nematodes stunt very sporadically throughout a field. And so if you've seen enough nematode pressure, you can walk through and go, yeah, that's maybe nematodes. And the goal is to be able to do that with a drone where you just do it all from your truck.
Any other questions? You didn't see much of a nitrogen effect on yield.
No,
Did you sample your fields before you planted?
we did. And I think we're going to need to take some deeper samples for the next season.
Because otherwise, it seems like this deal about nitrogen, it might just be a hoax, right?
Yeah.
Big nitrogen trying to sell you fertilizer.
The nitrogen question essentially covered it. Y'all did soil testing lab samples. Y'all sent them to 0 to 6 inches.
Yes. Yeah, we sent them to the soil lab down the road.
Yeah.
They gave us our recommendations based on our nitrogen applications. But I think we need to do probably Katie Lewis had suggested doing deeper sampling to be able to make sure our nitrogen rates were compatible.
Great job. Thank you.
Thank you.